All right, third and final example for our centripetal force, circular motion. We have a 1,500 kilogram car is getting off the freeway on a roundabout ramp. If the radius of the off-ramp curve is 100 meters and the coefficient of friction between the car tires and drive pavement is 0.7, what is the maximum velocity the car can go without sliding off the freeway? Now, this free body diagram is a little bit weird. We're going to look at the car from like if it was going into the page, meaning if this is our car, it's going into the page, we have the force of gravity down, the normal force up, and then the force of friction is actually the thing that is causing this centripetal motion. Because if you think about it, if we have a curve like this, and the car is here and it's rounding this curve, if there was no force of friction holding it toward on the street, right, on that curve and pointed towards the center of that circle, it would just slide right off the road tangentially, right? Because we know that that's the direction of tangential velocity. So because we have friction directed towards the center of the circle, it keeps that car on the road, and that's our centripetal force that's causing this motion, okay? So what we're going to do here is we're setting the force of friction equal to our centripetal force equation, which is mv squared over r. Now, I got a little ahead of myself. I didn't write down my givens. I'm going to write down my givens. M equals 1,500 kilograms. We also know that the radius of the curve is 100 meters, and that our mu, our coefficient of friction, is 0.7. Okay, so not much information, but they give us some. Now we know an equation for the force of friction that is mu times the normal force equals mass times velocity squared over r. Now I do want to mention here that this is actually the coefficient of static friction, because even though that car is moving, it's moving in the forward-backward direction, but the force of friction is all directed perpendicular to the motion of the car. So because of that, the car's not moving in the same direction as the force of friction, so it actually is the force of static friction. And we'll talk more about friction too in car tires and things like that when we talk about rolling. It's just a lot of crazy stuff when things are actually rotating and rolling and things like that. So that's why they only give us one coefficient of friction here. Now we know, since we're on level ground, normal force equals force of gravity, which is mass times acceleration of gravity. So I can plug that in for normal force here. I get mu times mg equals mv squared over r. And look at this. This is interesting. Our mass actually cancels out. And that's very helpful, because if we're finding like the speed limit, right, we're finding that maximum speed this car can go without sliding off the road. They have to post one speed limit for all of the different masses of cars on the road. So it makes sense that this mass would cancel out, because it would be way too complicated if they were posting like 50 speed limits. If your car is this heavy, you have to go this speed when coming off the freeway. If your car is this heavy, that'd be way too much. So mass actually doesn't matter because it cancels out in this equation. So we are solving for velocity here. So I'm going to multiply both sides by radius, and I get velocity is equal to the square root of mu times gr, and I end up getting velocity is equal to the square root of mu, which was 0.7, times our acceleration of gravity, 9.8 meters per second squared, times the radius of the curve, which was 100 meters. So 0.7 times 9.8 times 100, square root of that answer. And we get 26.19 meters per second. Now that is actually pretty fast to be rounding that curve. It's about 50 miles an hour-ish. Of course, this is for dry pavement. Now, if the pavement is wet, then it's going to be more slick, meaning that the coefficient of friction is less. So the actual speed limit that should be posted should be much less than this.